Hi everybody, and welcome to the continuation of exercise 5 on our list of final exam review problems. We already did part A of this problem in a previous video, so we're going to focus just on parts B and C in this problem. Okay, notice that parts B and C would like us to find a basis for the range and the null space of a linear transformation, okay, that they're giving us a formula for here. And our usual technique for doing that was to first find a matrix for this transformation and to use that matrix to help us to come up with the bases for these two spaces. All right, so if we want to find a matrix for T, we are going to need to choose basis. And in our case, we've got the same domain and the codomain, so we could just choose a nice basis for both of those. How about the standard basis? Okay, basis for second degree or less polynomials looks like 1x and x squared. Okay, and to build our matrix, we just need to take those three basis elements, substitute those in one at a time, and see what we get here. Okay, so starting with t of 1, we substitute that into our formula up here. We're going to get 4 times p of x, which is 1, plus 1 minus x squared times p of 1. And then p of 1 just means that we're thinking of that thing that we plugged in as being p. If you plugged 1 into the constant polynomial 1, you're just going to get 1 out. Okay, plus 16x times p of 0. If p is the function p of x equals 1, p of 0 is still going to be 1. Okay, and then we just want to take that and algebraically rewrite it so that it's a linear combination of the standard basis again. So if you just do the algebra, this works out to being 5 plus 16x plus negative x squared. Okay. And then we're going to do that same calculation for the other two basis vectors. So now we're ready to substitute x in here. And so our formula tells us we're going to take 4 times p of x plus 1 minus x squared times p of 1. So if you plug 1 in for x, you're just going to get 1. Okay, and then p of 0, that's going to be 0, because after all, our formula for p is just p of x equals x. Okay, do the same thing. Kind of multiply things through and regroup, and you're going to get just 1 plus 4x plus a negative x squared again. Okay, and then finally we're ready for x squared. If you substitute that in, we're going to get 4 times p of x, which is 4x squared, plus 1 minus x squared. P of 1 would be 1 squared. Okay, and then p of 0 would be 0 squared. Okay, and if you work that out, do the algebra, this time you're going to get 1 plus 0x plus 3x squared. Okay, and remember that our matrix is really formed by looking at the way that our outputs are represented as a linear combination of our basis in this case. So we can look at those coefficients and see that the matrix of our transformation relative to this basis is just going to look like this. First column is 5, 16, negative 1. Then 1, 4, negative 1, and then finally 1, 0, and 3. Okay, and just for convenience of notation, I'm going to take this, just give that matrix a name and call it A. So if I refer to A later in this problem, I'm just referring to the matrix of this transformation that we found. Okay, and the key to finding bases for both the range and the null space are to kind of get an echelon form for this matrix. So if you row reduce this, okay, I'm going to skip over the steps and trust that you could either do those or you could pull out your calculator or some kind of an app and figure out what this row reduced form is. Okay, one echelon form of this looks like negative 1, negative 1, 3, 0, negative 1, 4, and then finally 0, 0, 0. Okay, and we can look at that and kind of see where our pivot positions are in the first and the second column. Okay, so we have, I think, enough information here to get started thinking about part B, okay, which is finding a basis for the range. Okay, and we'll start by finding a basis for the range of L of A, okay, left multiplication by this matrix A. And you might remember that that comes down to noticing where our pivot columns are. Okay, the pivot columns in this case are the first and the second column, so that's telling us that we need to just look at the first and the second column of our original matrix, here and here. That should form a basis for the range of L of A. So we'll start by writing that down. So 5, 16, negative 1, and 1, 4, negative 1. Okay, now how does that help us to find a basis for the range of t, which is what we're really after? Well, there we need to remember that what we're really talking about here is coordinate vectors. Coordinate vectors relative to the basis that we've chosen for the codomain. In our case, the basis that we've chosen is just the standard basis. So all we really need to do to get the vectors in the basis for r of t is to just start here and to think of the 5, 16, and negative 1 as just being coefficients on our standard basis vectors one at a time. So 5 times 1 plus 16 times x plus negative 1 times x squared. Okay, and then doing the same thing for the other one, the 1, 4, negative 1. And it tells us then that these two polynomials, those are the corresponding basis vectors for the range of t. Okay, and so our answer to B then is just going to look like a set containing those two polynomials that we calculated. Okay, so we have answered part B there. Okay, let's remind ourselves again of what they're asking us in part C. Okay, they want a basis for the null space of T. Okay, so we're going to use kind of the same strategy that we did in part B. We'll first see if we can find a basis for the null space of L of A, this matrix. Okay, and that amounts to taking this reduced system that we have here and imagine setting that equal to 0 and writing down the solution set for that. Okay, so I'm going to do that in the space that we have here. Okay, if we set that equal to 0, and notice again where our two pivot positions are, how many free variables do we have there? It looks like we've only got one free variable, x3. All right, and if you take that and solve that for x2, it looks like we're going to get 4t. Okay, and let's see, what would x1 turn out to be? Okay, well, you can confirm my algebra here. x1 should turn out to just be negative t in this case. Okay, and so the null space of L of A, if we actually write it out, set of all solutions to the system that we have above look like negative t, 4t, and t, where t is in R. Notice that that can be rewritten as just t times negative 1, 4, 1. And so what we've really confirmed then is that the null space of L of A is just the span of a single vector that looks like negative 1, 4, 1. Okay, and so far what we know then is that negative 1, 4, 1 is a basis for the null space of L of A, a left multiplication by A. Okay, but we want a basis for the null space of T. How do we translate this basis for the null space of L of A into a basis for the null space of T? Well, again, the key is to think about coordinates. Okay, we're thinking of this negative 1, 4, 1 as being a coordinate vector. relative to whatever basis we chose for the domain. But again, the standard basis, that's the basis that we chose for both the domain and the codomain. So we're going to turn that into a polynomial by just interpreting the -1, 4, and 1 as being coefficients, okay, on our three basis vectors. Okay, and so what that means then is that our answer, okay, maybe so we can tell these apart, I'll call this B up here beta R for the basis for the range, and this one beta N for the basis of the null space. Just a little bit better notation there. So basis for the null space of T is just going to be a single polynomial in this case. -1 plus 4x plus x squared. Okay. And we are done.